Today we're going to talk about an important topic, which is numerical solution of elliptic equations. They're very common in our field. In the following lectures, when we consider certain approximations to our momentum equation that remove sound waves, we will get elliptic equations for pressure, or if we consider kind of incompressible two-dimensional flows of rotating fluid, we also can arrive to an elliptic equation for so-called stream function. So they're pretty common in our field, and they are relatively challenging to solve and require lots of resources usually. I mean computational resources in the models. And there are many ways to solving those equations. Some are more efficient, some are less efficient, but it's always challenging. So it's not a simple thing. So elliptic equations are basically differential equations of second order in space. In our field, that's what we solve, only in space. So there is no time derivative. And so the example of elliptic equation, so let's So the example is, for example, Helmholtz equation. Which has the following form: second derivative, some function phi dx square plus second derivative of phi dy square minus h phi equals to f, and h and f are some coefficients that can be functions of x and y. So this is a Helmholtz equation, and subset of that equation, Helmholtz equation, if for example h equals to 0, then this equation is called Poisson equation. So it's just second derivative, sum of second derivatives. Of course, it can be a derivative in height, in z, but I just skip it. Don't write it. So this is Poisson equation. It's a very typical equation in atmospheric science, in ocean modeling. And another example is when h equals to 0 and f equals to 0. Then it's called Laplace equation. So, so how you would solve it? First, let's use finite difference approximation of elliptic equation of this, let's say, of general Helmholtz equation, using second order approximation, second order accurate approximation for second order derivatives. For second derivatives that we used already in our previous lectures when we considered diffusion problem. So we have our nice grid, regular for simplicity here, kind of with equal times grid spacing like delta x, delta y, and we use indices I plus 1, I minus 1, j minus 1, j. So well, it's not quite equal delta x, but okay. So to approximate a second derivative with second order accuracy, we need 3 grid points. So we use these 3 grid points in this direction, and for another derivative we use 3 points in this direction. So this is our general pattern that we'll use for our Helmholtz equation. So let's write our Helmholtz equation in finite difference form. So we have phi I plus 1 j minus 2 phi I j plus phi I minus 1 j divided by delta x squared plus phi I j plus 1 minus 2 phi I j plus phi I j minus 1 divided by delta y squared. minus hij phi ij equals to fij. So this is our kind of typical approximation of elliptic equation in this case, of Helmholtz equation. So we could solve this equation. Of course, we assume that there are some boundary conditions. So like there are two types of boundary conditions in this case. Usually it's when phi is specified on boundaries everywhere, like say phi equal to 0. Or it could be a derivative of phi is specified everywhere on a boundary. Say there is no gradient on boundaries, like that's another example of that. So we assume that boundary conditions are specified. So we're not going to talk about those here. So how we can solve it? We can actually incorporate boundary conditions in the equation themselves for certain indices I and j, of course. So we could, of course, use some kind of direct method by considering some kind of rewriting this two-dimensional array as a one-dimensional array, is actually stored on a computer by introducing some index k. So k equals to I plus number of grid points in x minus 1 times j, where I and j is changed from 1. So you can actually, so if you use this, you can write basic equation like some matrix like a k k times this phi k equals to some right hand side some f k. So it's a system of linear equations or a matrix with a rank of nx times so something like that. So you have this system of linear equations, and if you try to solve it on a computer, if your nx and y are big numbers, then the matrix can be really immensely big. Like for example, if nx and y equal to 100, the matrix would be like 10,000 by 10,000, and you need to invert it. Of course, it's mostly zeros in that matrix, but still they kind of, unlike tridiagonal matrix solver, we cannot use a simple algorithm in two dimensions. But we can actually solve it in one dimensions easily. So in one dimensions, if you don't have this derivative, then it's you can use tridiagonal matrix solver to solve Helmholtz equation in one dimension using a Thomas algorithm. But in two dimensions, no luck. In three dimensions, even less luck. So direct method in this case doesn't work. Although there is another direct method that we're going to consider a little bit later. But usually for this kind of equations, especially when you have coefficients here that are also functions of x and y, then there is basically only one way of solving this equation. It's using iterative methods. So use iterative methods. So let's consider some examples of those methods. For that, first let's rewrite this equation in the following form. Just phi ij equals, and also let's assume that delta x delta equals to delta y equals to delta. Just make it just simple expressions, although it's not critical. So it's 1 divided by 4 times delta square h ij and here is going to be our phi I plus 1 j plus phi I minus 1 j plus phi I j plus 1 plus phi I j minus 1, and here we'll have minus and here we'll have plus minus Fij times delta squared. That should be something like that. So, and iterative procedure, now we can use, let's use some iterative procedure to this equation. So the first method is so-called the Jacobi method. So Jacobi method, which is very simple. In that method, it's the following. So next iteration, nu plus 1, so nu is iteration, equals to 1 over 4 plus delta squared Hij. And here you have the same expression, but evaluated at the previous iteration. So it's iteration nu. So very straightforward. You just go through all your through your array here, and and then you use values. So value here you evaluate at as the next iteration, and you use all these 4 values around to evaluate like that you computed already in the previous iteration. And you stop it when say some norm, so let's say max over ij of phi ij nu plus 1 minus phi ij nu. So maximum everywhere on the grid smaller than some epsilon, which you choose. And then you stop your iterations, and solution has been achieved. So this is a very simple method. The drawback of that method that you need actually 2 arrays for phi, right? So there is some penalty for storage, because this is your new iteration and you use your previous iterations, and of course if you don't, so you will be overwriting, if you use the same array, you will be overwriting values that you previously computed. And actually that's maybe a good thing, and because then you instead of using just new, you would use already values that are already closer to the truth, presumably. So, and that's basically a very small modification, which is to the Jacobi method, which is called Gauss-Seidel method. Gauss-Seidel method. And Gauss-Seidel method, basically, you use this one array only, and you override values that you just computed as a new iteration using this formula. So if you move by increasing indices I, and then after that you kind of scan like that, increasing after you went through all i's, you move one step up to j, and so on. So you already would update this guy I minus 1, so it's going to be plus 1, and this guy too. So this is modification. So now you can use only one array instead of using 2 arrays. So you make you say some storage for memory storage, but and also actually it turns out that this method is about twice as fast, converges twice as fast, so requires about twice a smaller number of iterations than Jacobi method. So so that's very so it's Jacobi method. Instead of using Jacobi method, we just go ahead and just use Gauss-Seidel. So it's basically it's a reuse already found solution. at nu plus 1. So that's basically it. So those are, but still the convergence of even, and you can use the same norm, of course. The convergence, though, of those methods is relatively slow for a variety of reasons. I'm not gonna, this is not a applied mathematics class, I mean, strictly. So, but there is some theoretical understanding why it happens. So the convergence rate or number of iterations to achieve given epsilon is not that great. So you need a relatively a lot of iterations. So there is another method which is a modification of the Gauss-Seidel method, which is called successive over-relaxation method. So let's see. Let me erase this. Oh, there is the whole thing. So successive over-relaxation, that's much faster converging method. So let's see. Successive over-relaxation it's the following. We write our solution as modified as the following: ij nu plus 1 equals to 1 minus omega phi ij nu plus omega divided by 4 plus delta square. And here you have our previous expression, phi I plus 1j nu plus phi I minus 1j nu plus 1 plus phi I j plus 1 nu plus phi I j minus 1 nu plus 1. So we basically like use this as in a Gauss-Seidel method, but now we see we added this this term here with this omega, which is a weight. We just basically well, and of course we forgot and here actually it should be like this, divided by 4 plus delta square plus delta square phi ij. I believe it's something like that. So when the idea is the following, like when iterations are convergent to true solution, the difference between iteration nu plus 1 and nu becomes very small. So these two values kind of the same. So then you see that this, if multiplied by omega, and this one, so basically this guy times 1, they cancel left and right hand side, this and that, and then you have omega times solution equals to omega times this right hand side, so that looks like this. I mean in the previous equation. So basically then it's true solution, but so it's kind of looks a little bit different, but actually when it converges it looks the same as your original Gauss-Seidel equation. And this omega, this weight, is called relaxation parameter, and or over relaxation parameter. And this parameter should be theoretically shown that it should be greater or equal than 0 and smaller and equal than 2. Otherwise, this algorithm would be unstable, wouldn't converge at all. So, so this is over relaxation parameter. And this parameter usually found because here I wrote a simple one expression, but if you have some coefficients here in front and so on, and maybe the different delta x and delta y that changes with position, with changes in space, then your omega should be found experimentally. So basically, you just take some right hand side, and usually like maybe solutions that already known, or we just take your some initial conditions and then see how fast it converges to your solution, and then modify your omega a little bit, like add, like say you start from 0, or actually from 1, let's say, and then you basically change. Sorry, of course it cannot be 0 from 1. So you start from 1, for omega equal to 1, this one is basically just Gauss-Seidel method, right? Omega equal to 1 Gauss-Seidel. And then you just add, say, 0.1 to omega and 0.1 and see how many iterations it takes to reach your some convergence using some your epsilon. And then you may find some omega which produces your fastest convergence, and then you use that in your model for the same kind of configuration of parameters. So basically some tuning is required. You need to tune this omega to obtain fastest convergence. Of course, there are some formulas for simple cases, like our case, when delta x and delta y are constants, and I could of course write this formula, but in reality, usually it's very rare. In reality, it's very rare that you have this kind of simple setup. Usually, you have maybe different delta x, delta y that change in space, or you have some coefficients. So in that case, it's only experiment can show you which omega. So this method is called again successive over relaxation, and it's very popular iterative procedure. Okay, so now there are other methods, so-called direct methods, and those direct methods. So direct means that no iterative procedure is involved. The solution is precise. So you can find precise solution using this direct method. And it only works in a very few special cases of this equation. Namely, it works when you have equation, like elliptic equation like this, like Helmholtz equation, but your delta x and delta y's are constant, not necessarily the same, so delta x can be different than delta y, but they should be constant everywhere. And also coefficients should be constant, not changing in x and y. If you have such special condition, and that such elliptic equations, for example, arise from using, say, Cartesian grid with constant grid spacing, when you get some Poisson equation for pressure or Poisson equation for stream function. So those cases are special, and in those cases you can actually use direct method using Fourier decomposition. So let's talk about that a little bit. So what's so let's say that so let's consider two-dimensional. Well, let's just consider just theoretical kind of case of, say, Poisson equation. So let's consider Poisson equation for simplicity. So for Poisson equation, you have the following equation. And so you can use Fourier decomposition by assuming, and that only works when delta x equals to delta y and equals to, well, in this case there is no delta x yet, right? So just generally, like if you have this equation, theoretically how you can solve it using Fourier harmonics. So you basically write your solution, that your solution equals to sum of some Fourier harmonics, say over wave numbers k and m, such that this amplitude k, m, e, this our imaginary or our complex exponent. So we have kx plus my. So this is just Fourier harmonics. Because equation is linear, we can easily use Fourier analysis here. And so this is we transform our function phi, even though we don't know yet, but it's just formally, let's write it like this. Function f we know, so we also transform it as the following, as sum of wave numbers k and m, f, so here is of course amplitude km e I kx plus my. So now if you substitute these two representations in Fourier series to your original equation, you will see that when you differentiate that, and also using the fact that each of those Fourier harmonics are orthogonal to each other, it means that they're independent from each other. So you can, if you substitute, you may get the following equation, that minus k square plus m square phi km equals f km. So you just substitute, you assume that Fourier harmonics are independent, so you basically solve it for each of these for each of those harmonics, and then you cancel by this complex exponent, and as a result you get this very simple equation from which you can find that your amplitude Fourier harmonic amplitudes, and these amplitudes you know because you know f. So you have that it's equal to f divided by minus k square plus m square. So this is basically the idea. So first you do your Fourier analysis, you obtain those coefficients, Fourier coefficients. For f, you don't obtain for phi because you don't need them. You compute them by taking Fourier coefficients for function f and dividing by these wave numbers. And then after you founded these coefficients, you do analysis, synthesis. So you reverse your Fourier analysis to synthesis and obtain your solution phi. So using this. And basically that's it. So you immediately get the exact precise solution. And then you of course sum all these harmonics. Like when you do this analysis, of course, the synthesis, you basically automatically sum them, and you obtain your actual function. So this is if you do it analytically, but of course we do it on a computer, and on a computer we don't have these continuous functions, but we still can do Fourier analysis on even on functions that are not continuous using so-called, instead of kind of truncated Fourier series. So let's see how we do it. So let's first consider one-dimensional case as the simplest one, just to demonstrate how it's done. So in 1 dimensions, 1D problem. So we have find a difference representation of our Poisson equation as phi I plus 1 well, let's not use I because we have this complex exponent there with I too. So let's use k. Phi k plus 1 minus 2 phi k plus phi k minus 1 divided by delta, or delta x squared, equals to right hand side phi fk. So this is final difference. Well, in this case we don't really even need to use Fourier decomposition because this is three-diagonal solver problem, right? So you have 3 points and you can use your fast Thomas algorithm for that. But I mean, of course, I wouldn't use Fourier decomposition for this problem for one-dimensional. I would use three-diagonal matrix solver, but just to demonstrate the method. So, because we will use the same method for two-dimensional case when we cannot use this three-diagonal matrix solver. So first, so our k is from 0 to nx minus 1. So we use the zero index here. So our Fourier decomposition looks the following. Fourier series, phi k equals to sum from n equals to 0 to nx minus 1 phi n e to the power I 2 pi n k divided by nx. And here is Fourier amplitude, Fourier harmonic amplitude. So this is already inverse transform, right? If we know those Fourier coefficients, we use this inverse Fourier transformation to obtain your solution in those grid points. So now let's substitute this solution into our differential equation in our finite difference approximation. So what we get is like we did before in when we considered stability analysis using von Neumann method. Remember when we substitute and it's very similar. So we have phi n e I 2 pi n divided by nx, and here I already divided by e to the power common in the by this quantity. So here is k plus 1, so only 1 will remain. Here it will be gone, and here it will be gone. So I already divided by e to the power I 2 pi n divided by nx. So it's minus 2 phi, well, it's again the same amplitude. So for each harmonic, because they're independent, we can write this one equation. So this phi n times minus 2, and here it's going to be plus e to minus I 2 pi n divided by nx, and equals to this Fourier harmonic for right hand side, which is kind of written similarly. And these Fourier harmonics we actually know, because we take our function f, which we know, and we use Fourier analysis or Fourier transform to compute this coefficient. So we know this, guys. We don't know these guys. But for this, you can see actually it's similar to our stability analysis. It's e I alpha minus 2 plus e minus I alpha, remember? Something like that. So e to the power of I alpha equals to cosine alpha plus I sine alpha, and so cosine is an even function, so cosine of minus alpha equal to cosine alpha, and sine is actually odd function, so cosine of minus alpha equals to minus cosine alpha. So if you do that, you will get that it's equals to 2 cosine alpha plus minus 2. So in our case, then we have, just instead of alpha, we use these guys. So we have that phi n Fourier harmonic amplitude equals to f coefficient, Fourier coefficient, divided by 2 cosine 2 pi n divided by nx minus 2. So instead of, remember before that we had like a wave number k square plus, like wave number k square in one-dimensional case here. So this is our finite difference representation of that coefficient. So you see now we have cosine. In continuous case it wouldn't be cosine here. But in this finite difference approximation we get this. So now the algorithm is the following. So first compute, so do Fourier transform of your right hand side. So compute these f coefficients, and usually you do it using fast Fourier transformation routine. You don't of course write it yourself. Any mathematical package on the computer has this fast Fourier, so-called fast Fourier transformation routines, and for it to be fast, the number of grid points should be a certain number. It cannot be arbitrary. Usually it's like power of 2 or some product or some number which is as a product of some kind of numbers like 2, 3, and 5, but not 7, for example, and so on. So if you follow those rules and you can use this Fourier decomposition is very fast. It's very optimized on the computer. So fast of FFT. So you using FFT, fast Fourier transformation. And second step, you compute. So compute phi. So from your Fn, you compute phi n using this formula. And from that after you're done, you do inverse FFT to compute your solution. Phi already on grid, on a physical grid. So that's basically a very simple procedure. Similar procedure can be done in 2 dimensions, or even in 3 dimensions. As the following, we just know that that's why it's very important not to have mixed derivatives, because you have this derivative in x and derivative in y independent from each other, so they're linear with respect to each other. And in that case, you can actually use first Fourier in one direction, and after you obtain your Fourier coefficients, you actually treat them as a new one-dimensional. If it's 2-dimensional, now you have for each Fourier coefficient, it's actually a function of your second index. So you have a one-dimensional problem in another direction, and you repeat the same procedure to find another Fourier indices, and then you do reverse twice. So let's write it more kind of in more detail. So you now you have now you have two-dimensional finite difference approximation of your Poisson equation. So 2D. So it looks like the following: I plus 1 j minus 2 phi ij plus phi ij plus 1 minus 1 divided by delta x square plus phi ij plus 1 minus 2 phi ij plus phi ij minus 1 divided by delta y square and equals to fij. So this is two-dimensional Poisson equation, and you basically do the same thing, but now you do it First, you apply to Fourier analysis to phi. So you have this ij. You apply it only along the index I for each j. So for given j, you do this Fourier decomposition in this whole kind of stencil along the direction I. So using FFT, fast Fourier transform, you produce now indices f, m, j. So you see m is your Fourier coefficients. For each I, there are m Fourier well, there is correspondence in Fourier space of phi m. So after that, you and so your equation, this term. So this now equation looks like the following. It's phi I j plus 1 minus 2 phi. Well, actually, it's not I. Now it's actually phi. Let's do it first like this. So first you do this. So these guys will all indices I will be transferred to index m, and you kind of assume that, well, we don't yet know these phi's, right? We just basically now we just substituting. What do you actually do? In this stage, you actually transform right hand side. This is what in reality you do, right? So you have f, you transform to indices. We just substitute this in this, and then we have the following equation that this thing becomes phi mj times, as before, cosine 2 pi m divided by nx minus 2 cosine divided by delta x square. So this term becomes this. So only one dimensional. You see, now we will have only this guy. And here it's actually all these I indices becomes m indexes. So it's phi m j plus 1 minus 2 phi m j plus phi m j minus 1 divided by delta y squared equals to this right hand side, which is Fourier harmonic m j. So you see, you transformed your equation in the direction I. You transformed it, and now instead of this 3-point pattern, you have only just 1 point, and that's why you and now you have 3-point pattern. So in principle, you can use your Thomas algorithm to do that, but actually in reality, for each j you need to use this Thomas algorithm. I don't know if it's actually worth it, because FFT is extremely fast procedure. So it's possible that actually that FFT, starting from certain size of your grid, probably for very small ones, maybe I don't know which one is more efficient, but you could just continue doing FFT. So now you use your FFT again, but transforming along the j direction. So you take your indices and transform using FFT to your second index. So now it becomes like 2 hats here. And so, and here is should be m of course. Fm j becomes f double hat f mn. So you do this FFT transform of, but of course you don't do it in reality. You don't do it on phi because you don't know phi yet, but you do it on f. And after that, now your second expression for second derivative becomes expression like this. So you have equation that f m and j mn equals to f double hat mn divided by this product 2 cosine 2 pi n divided by nx minus 2 divided by delta x squared times times 2 cosine 2 pi. So this one is m, so n divided by ny minus 2 divided by delta y squared. And so this one becomes double head. Yeah, so for each m and n you do this, you compute this coefficient, and now you do inverse. So first you compute so now you know this Fourier coefficients, and now you do inverse transform on phi. So you do next step, you compute phi mj, so you have your phi mn, and you use FFT inverse FFT. And on computer, this FFT is just basically function call. So one of them is called, like, if you supply some flag, it does analysis or direct transform. If you supply some flag, say equal to, I don't know, -1, it will do it inverse transform. So it actually knows how to do it. So it's black box for you. That's the beauty of FFT. It's a black box routine, and very easy to use. You cannot code it yourself. It's very complicated. So it's 5mj, and then from phi mj, using inverse FFT. So this is inverse FFT in y, this is inverse FFT in x, you obtain your solution ij. So using this double heads to one head, single head, then from one single head to your solution. And you're done. So this is, it's called direct method. It's produced, no iterations are required. And this is a good thing. Direct method, if they're simple, if you can actually use them, use them. They're very powerful because iterations are always iffy. Your solution may, for some reason, have some slow convergence, or it may not, like, I don't know, due to some crazy stuff that's going on in your domain, some other processes, it may actually slowly converge in certain places, or even if you have some instability developing in your solution, or some, I don't know, maybe nonlinear noise or something, it may actually slow down the convergence very considerably. So you never know how long, for example, your model will take to run, because it's constantly kind of, it's a moving target, because the number of iterations constantly is different. And in some situation it can happen that it just won't converge and you will have to stop. Direct method, it's guaranteed. It may be more difficult to code. It's more tedious a little bit, but you do it once, and as long as you implemented it, direct method always beats any iterative method, because, well, it's direct method. You always get your exact solution, no matter what. No iterations. So it's always preferred. Unfortunately, in many cases, our domains and our grids are not really Cartesian, nice kind of grids, or even not latitude, longitude grid. When you also, in certain situations, you can use FFT or some other functions, like there are some so-called spherical harmonics that you can use on sphere, similar way to fast Fourier in using cosine sine functions, like in this classical Fourier analysis. But you can also use some other base functions, so-called base functions, Fourier functions that could be, like, say, spherical harmonics and so on. But the idea is basically the same. And if you can use a direct method, use it. It's worth it. So I think it's enough for this lecture.